So another thing is what Jörg brought out, so what if we want to have an anytime learning algorithm, right? So anytime learning algorithm. So anytime learning algorithm. So we call that an algorithm anytime when you have like a fixed policy that says for a red line doesn't explicitly depend on the time span. But if you have like some pi such that, for all hypotheses in the hypothesis class, the crash of pi with respect to this hypothesis, gamma goes to 0, gamma goes to 1, and pi doesn't depend on gamma, it's just fixed policy. So typically, the UCB algorithm I described before doesn't work anymore. So, but instead we could have some algorithm, because like we had this k, which kind of depended on gamma. Right? Instead, k could just depend on time. So we have basically, think about it as like we have our full hypothesis, and then there's this hk, but we're kind of increasing the k over time. So it means that like over time, we gradually start considering more and more hypotheses. So this means that when we kind of go to the step of following the optimal policy, right? So like algorithm was like something like, it has like compute confidence set, right? And then compute confidence set, and then like choose some hypothesis out of the optimistic part of the confidence set, and then follow the optimal thing, and then like if H is falsified, then we go back to step 1, right? Something like this. So in previously, when we reached this line in the algorithm, as long as H wasn't falsified, we would continue this forever. Now this doesn't work anymore. Now we might, like as this class goes, there might appear some hypotheses that are even more optimistic in this H. And then eventually we need to switch and try one of the new, more optimistic hypotheses. So what this means is, for infra-Bayesian haggling, it means that if we have those players that they kind of win here and they're in some equilibrium here, but now suddenly one of them can get like some new hypothesis which has a higher payoff, so it stops cooperating with the other and starts trying to this new hypothesis. And the other gets their hypothesis falsified, so it's not also switches. So like the whole equilibrium kind of falls apart, and they all start running around again, trying to find some new thing. So yeah, what happens? So I don't have like a very good analysis, but it seems to me that there have to be some set of assumptions you could place on the algorithm, such that in the limit, right, as time goes to infinity, you will spend most of your time in equilibrium. Because what happens is the system, and then there's like equilibrium, right, and then there's not equilibrium. What's a good word for this? Exploration. Right, the system is like in two states. Either the agents are just like going from a hypothesis and falsifying it, or they have like a hypothesis they're happy with and they're sticking with it. And the system is like moving all the time between those two states. Like it reaches there, but eventually some more optimistic hypotheses appear which move the system here, then they again find like a new equilibrium, they go back here. So it seems that there has to be some choices we can make in the algorithm can guarantee that we spend most of our time here, right? Like the time to go here is kind of is short, relatively. The time to go here is long. And in the limit, most of the probability mass is here. However, we can also justify this kind of assumptions not by referring to multi-agent, but just like in terms of like the algorithm, well, in itself as just kind of more abstract consideration. I don't know, but I think it would be a very interesting problem to see if we could find some natural set of assumptions that can be somehow justified from outside this whole framework, that in this framework would lead to this kind of conclusion. So, I mean, it seems like this thing is not like fully motivated. I mean, it seems like you could kind of try to kind of generalize the logic of what's happening and saying, it's not just about games, but it's about environments that can enter particular states in which like you like maintain some equilibrium, but you can also but those states are kind of transient, like you can sometimes exit them and you can find them again. So you can try to somehow formalize in this type of kind of capricious environments that kind of locally follow some regular laws, but on a longer time scale, the law might change occasionally. And maybe we can somehow formalize this and somehow do learning algorithms for such capricious environments would have this kind of policy. I don't have a reverse in here. So for multi-agent, it's kind of even more kind of chaotic sort of ish, right? Because like for multi-agents, we'll have maybe two agents form a coalition, another three form a coalition, and another two form a coalition. But now this agent suddenly decides to do something else. So this entire part of the coalition falls apart. Those two keep doing whatever they're doing, they don't care. But those are not running around again, and then like the system crystallizes and maybe it falls out into some new configuration. Maybe now those two decided to form a coalition, and those three decided to form a coalition after. I don't know. So you see that there's a lot of equilibrium. So that's just now there's like many equilibria. Equilibrium 1, equilibrium 1, equilibrium 2, equilibrium 3. And the system is kind of moving around between those equilibria. And not all the errors are possible. We can go from 1 to 2, and from 2 to 3, but you cannot go directly from 1 to 3. I don't know, there could be all sorts of possibilities. So, in the middle is going through some kind of an exploration state. But here, like, if somehow this thing works, then here probably also most of the time would be spent in equilibrium. But they would be kind of shifting between different equilibria, right? So there's some kind of a very interesting dynamics here. It's some kind of a Markov chain of different equilibrium. And one speculative idea I have, which currently is like, not doesn't have like a very solid analysis, but seems kind of something that might work, is that maybe this is actually good, because maybe this will allow the agents to select better equilibrium. So if you recall before, we had this picture, right, with like the 2/3, 2/3, 1/3, and the 1/2, 1/2. So now, both of them are like possible equilibria of the system. You might spend some of the time here, some of the time here. But now we can kind of speculate that a reasonable learning algorithm would have the property that if it's in an equilibrium which has a higher payoff, then it would be more reluctant to switch to a different hypothesis and like forego this equilibrium. Whereas if it has a lower payout, then it would do so with a higher rate. So it's possible that we can add this type of assumptions to the learning algorithm, so that the kind of transition rates in this chain will guarantee that, in the limit, we'll end up converging to Pareto efficient equilibrium, maybe, or I don't know, say something to the yeah, and yes, something else I wanted to say about this.
This is true already in the two-player game. If one of them locks into a maximum, but then a new hypothesis comes in and they're like, oh, maybe I can try a new password that I haven't tried, and can allow coming out with sort of bad decision.
Yeah. Mm-hmm. Yeah, so sort of insights and kind of thinking about this led me to an interesting mathematical question, which is kind of interesting in itself, and I don't really know the full solution to it. So in general, suppose that you have a Markov chain, or you have some space, and you have some Markov chain, and let's suppose we're thinking of it as a continuous time Markov chain. So it means that like every one of those states has a particular rate to go to other states. But let's imagine that those rates are all like very, very like different from each other in magnitude. Right? Like for example, if those rates are like x1, x2, x3, x4, then suppose we know something like x1 is much bigger than x2, much bigger than x3, much bigger than x4. Right, so the question is, can we always, given such a system, like say where the equilibrium is going to be, just like by looking at this kind of at this partial and this kind of order in the set of rates. So that this kind of, instead of this kind of sort of continuous problem, it becomes just a purely combinatorial problem. There's now this kind of directed graph. There's some order on the edges, and then this order is supposed to define on which. And like from this we want to calculate or somehow characterize on which vertices the equilibrium can be supported. There's actually what I found is there is examples where this information is insufficient, but you need to do something like compare x1 times x2 to x3 times x4. So this is not. So it's not true that just having this information is enough to choose one vertex. There are situations in which, like even if it's all connected, like if there's some component that's kind of work, even if everything's connected, there can be situations in which the order of the products is important. But maybe we can like generalize this and have like some kind of, it becomes like some kind of an algebraic object, where like we have kind of some kind of order on I don't know, something like the commutative model generated by those ages, something like that. And from this order, we kind of want to determine. So the conjecture is that if there is some order on this kind of commutative monoid, then there's one vertex, and the graph is like connected. There's one vertex which has to where the equilibrium has to be. But I don't know. This is kind of interesting. Just kind of an interesting mathematical question. One last thing I wanted to talk about in this topic is that so far we only talked about repeated games, right? But what if we want to do some sort of one-shot games? So if you read like all of this kind of less strong discussions of like updated decision theory and stuff, there was this kind of idea that one-shot prisoner's dilemma, if both agents see each other's source codes, then they should be able to cooperate. Because then you can kind of know that. So can we kind of get a learning theory to support this? So the one problem which is obvious is that the learning theory doesn't work very well with one shot, right? Because to have learning, we need to have some kind of a sequence of accumulated evidence. So how do you do something which is one shot, but there's also learning? And so in one kind of thing that nice potential solution to this is what I call population games. Imagine that instead of having some fixed set of players, we have some enormous number of players. Like we have populations of players. Like instead of for a two-player game, we have like two populations. Population 1 and population 2. Each of those populations has a very large number of agents, and we like consider the limit in which those numbers go to infinity. So the thermodynamic. And what happens in the game is that every round they're kind of paired off randomly. So each agent gets someone to play against in the other population. And now every encounter like this is one shot in the sense that they're not going to see each other ever again because it's so large. But each agent is still experiencing a series of encounters. So there is some learning. And there is some simple result I had about that, which kind of Viktoria Malyasova wrote out in the previous cohort, that it shows that like you get some kind of a dynamical system here, and this dynamical system is guaranteed to have at least one fixed point, and all the fixed points are guaranteed to be Nash equilibrium of the game. Like if you assume certain assumptions, certain simple assumptions about the learning problem. But okay, here we want to do something else. Here we want to have the agents see each other's source code, right? So what does it mean to see each other's source code? So it means that, so in this case, the source codes are kind of fixed. So seeing the source code is not that interesting. But seeing the history, so every agent kind of comes into the pairing with its own history of previous encounters, right? So now we could imagine, for example, that each of them sees the history of the other. That's one version. See each other's history. Another version, which I think might be actually simpler to analyze, is that they see each other's working hypothesis. Right? Because we have this algorithm that selects a particular hypothesis in every stage. So what if during the interaction they get to see which hypothesis the other is following before choosing their own action? And I think that so I don't actually have a result. It seems much harder to analyze, but I think that there's some chance that we can get some nice result from this if we use metacognitive agents. Because like a metacognitive agent can do some kind of a quieting thing which says, if the other agent is using a working hypothesis, which is the same as the working hypothesis I'm using, then something, or like constructions of this form. And this kind of thing can allow you to define hypotheses in the hypothesis space, which have the properties such that if you meet another agent with a similar type of hypothesis, then you would be able to like cooperate with it. But this in itself still doesn't solve the problem, because the way infra-Bayesianism works is like, to get any sort of convergence, your hypothesis needs to have like some particular expected utility guarantee. And a hypothesis only guarantees that if you meet an agent that's following the same hypothesis, then you get some good payoff. That doesn't guarantee you anything, since you need to also lower bound the probability it will actually meet this other agent. So you get some kind of non-trivial dynamics where, like, you have some hypothesis and some fraction of the population is following it, and what you're trying to prove is something like, well, kind of the fraction of agents that will be following this kind of hypothesis will kind of increase over time, because the larger it is, the more beneficial it becomes to follow this hypothesis. But like, I don't know how to, I don't have like a way to actually like formalize it that I'm especially confident of, but it seems that, like I said, this seems like a much harder analysis than this repeated game, but it seems like there's some chance to get a result for this kind of formula.